Let's look at applying Leibniz theorem in some problems. First one, let's see x cube EAX. Let's say u is equal to EAX and v is equal to x cube. Now v1 would be what? 3x square, v2 is 6x and v3 is equal to 6. Now v4 would be 0. Now as far as u equal to EAX is concerned, u1 is equal to, now see, if you remember the nth derivative standard form, then it's not a problem. You can directly write it, a to the power of n EAX. But suppose you don't remember this, not to worry, just keep doing it normally. AEAX, u2 is equal to, a again comes down once, so a square EAX, u3 A3EAX. So do you notice these two are matching? So as you go down, what will happen is un would be a to the power of n EAX. Now that we have this in place, let's apply the Leibniz theorem. Now remember, nth derivative is equal to nc0 unv plus nc1 un minus 1 v1 plus nc2 un minus 2 v2 plus nc3 un minus 3 v3. Now let's do the resolving of this. nc0 is 1, un is a n EAX plus nc1 is n, un minus 1 would be a to the power of n minus 1 EAX, v1 is, by the way, I missed this, v is x cube plus nc1 is n, un minus 1 is a n minus 1 EAX plus no, and v1 is 3x square plus nc2 is n into n minus 2 by 2 times un minus 2 is a to the power of n minus 2 EAX, and v2 is going to be 6x plus, now nc3 is n times n minus 1 times n minus 2 by 6 times a to the power of n minus 3 EAX, and this would be 6. Now simplify. Now simplifying this, x gets cancelled, this 2 and 3, and now what we'll do is we'll take out what is common. Now what is common is EAX and a to the power of n minus 3 is common. Now a square, if I put, what happens, n minus 3 plus 2, minus 3 plus 2 is 1, so n minus 1, so which is wrong, we want n, so this should be 3, a cube x cube plus n times a to the power of n minus 1 is there, so if I say square, what happens, minus 3 plus 2 is minus 1, so n minus 1, which is what we want. Okay, a square and then 3x square plus, next is n times n minus 1 a to the power of, now what, a to the power of 1. If you notice 3, 2, 1, it is reducing by 1, so a to the power of 1, and what else? N minus 1 and 3x. This one plus n times n minus 1 times n minus 2. A to the power of n minus 3, we have taken it out. So 1. EAX is out. So that is what we are left with. So now it's just a question of rearranging the terms within the elements within a term. So this is the nth derivative. Okay, now let's look at the next one. Let's say y is equal to x to the power of n log x. Now here the question is, show that y n plus 1 is equal to n factorial by x. Now this itself should give you an idea that at least one differentiation you have to do it independent of the Leibniz theorem. Okay, so let's differentiate this. So y1 is equal to xn as it is and 1 by x plus xn differentiation. So n x n minus 1 log x as it is. Okay, now let's take the LCM. X to the power of n plus n x, and we have to multiply it with one more x. So n minus 1 plus 1 will make it n log x y1. Now this x, we can take it to the other side. xy1 is xn plus n, and x to the power of n log x is nothing but y. So y. Now let's apply Leibniz theorem on this. Okay. Now xy, so y1, so nc0 unv plus nc1 un minus 1 v1. Yes, there are only two terms. So now is equal to x to the power of n is going to be what? N factorial. Even if you don't remember it, you should be able to very quickly derive it. So first differential n x n minus 1. Second derivative would be x n minus 2. Third one will be n into n minus 1 into n minus 2 x to the power of n minus 3. So this will keep reducing. So it will reach up to 3 times 2 times 1. So it will be n factorial. And this will reach 0. So this is 1. So you are left with n factorial. Plus this is nth derivative. So this is straightforward. N times nth derivative. Now here we have to do a little bit further work. nc0 is 1. un, let's say u is y1. So in that case, what happens? Un would become n plus 1. Why? Because we have already differentiated it once. So this would be n plus 1, and v is x, plus nc1 is n, and this would be what? This would be y. One second. This would be n plus 1. Right? You need to be very careful here. U n plus 1 v. So this would be n. Right? So that's how it will go. So here it will be yn. v1 would be x. Differentiation of x is 1, which is equal to n factorial plus n yn. Now 1 we can remove it off. So nyn and nyn gets cancelled, and we are left with yn plus 1 x is equal to n factorial, which means n plus 1 is equal to n factorial by x, which is what we had to show. Yn plus 1 is equal to n factorial by x. Okay, now let's look at the third one. Y is equal to ex log x. Now u, let's say, is ex and v is log x. Now if it is e to the power of x, it is not going to change. So u1 is going to be ex, u2 will be ex. Similarly, un minus 1 is equal to ex and un is going to be ex. Now here v would change. v1 would be 1 by x, v2 would be minus, just for your understanding, I'm going to take it up, so minus 1. So now if you differentiate it, you will get what? Minus 1, minus 1, minus 1, so minus 2. So which means x square. v3 would be what? Now again I'm going to take it x minus 2. So minus 2 minus 1 plus 1. So 2 by x cube this will become. v4 would be 3 to 6. So 6 minus 6 by x4. So its nth term would be, Vn would be minus 1 to the power of n minus 1 factorial by x to the power of n. Okay, now let's apply the Leibniz theorem. So nth derivative would be nc0 unv plus nc1 un minus 1 v1 plus nc2 un minus 2 v2, and this would go on, and the last term would be ncn uvn. Now nc0 is 1, un is eax, v is log x, plus nc1 is n, un minus 1. This doesn't change. This is not eax, it is e to the power of x, e to the power of x. Nex and v1 is going to be 1 by x plus n times n minus 1 by 2. un minus 2 is again ex. v2 is going to be minus 1 by x square plus dot 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 dot, and the final term would be ncn is 1, u is again ex, and v is minus 1 to the power of n minus 1 times n minus 1 factorial by x to the power of n. Now what? Now simplify it. Take out whatever is common. So here common thing is only e to the power of x. So log x plus n by x minus, because of this, minus 1 by x square, n times n minus 1 by 2x square plus dot 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 plus minus 1 to the power of n minus 1 factorial by x to the power of n. So this is the nth derivative of e to the power of x log x. Okay, so fourth one, y is equal to x square e to the power of x cos x. Now here, if you think about it, we can convert it into three functions, but we really don't know how to handle three functions. So we take this as one function and this as one function. So here u would be e to the power of x cos x and v would be x square. v1 would be 2x, v2 is 2 and v3 is equal to 0. Okay. Now this is the tricky part. There is a standard form for ex cos x. So let's very quickly look at that. Now let us say y is equal to e to the power of ax cos bx plus c. Remember the standard form. So nth derivative is r to the power of n eax cos bx plus c plus n theta. This derivation we have already seen in standard forms of nth derivative. Okay, now here r is equal to square root of a square plus b square and theta is equal to tan inverse of b by a. And here in this a is equal to 1, because remember what we are looking at is e to the power of x cos x. So here x is there but b is not there. So 1, a is not there. So 1, c is not at all there. So it will be 0. So a is equal to 1, b is equal to 1 and c equal to 0. So which means our nth derivative for e to the power of x cos x is going to be what? R to the power of n. So here r is what? A and b are 1, 1. So 1 square plus 1 square is 2. So square root of 2, which can be written as 2 to the power of 1 by 2. But n is already there. So n by 2. E to the power of ax. Now a is 1. So we don't have to write a at all. So e to the power of x. Cos b is 1. So x. C is 0. So we don't have to write it. N theta. So n theta is n tan inverse of b by a, that is 1 by 1, which is 1. Tan inverse of 1 is nothing but pi by 4. So un would be 2 to the power of n by 2 e to the power of x cos x plus n pi by 4. N minus 1 would be what? Now this is easy. You just replace all n's with n minus 1 e to the power of x cos x plus n minus 1 pi by 4. Now that we have this in place, remember we have to just look at 3 terms. Fourth term anyhow becomes 0 when we apply the Leibnitz theorem. So let's apply the Leibnitz theorem. So nth derivative is nc0 un v plus nc1 un minus 1 v1 plus nc2 un minus 2 v2. Now 3, if we go, it becomes 0. Now nc0 is 1, un is what? 2 to the power of n by 2 e to the power of x cos x plus n pi by 4 times v, that is x square, plus nc1 is n, un minus 1 is 2 to the power of n minus 1 by 2 e to the power of x cos x plus n minus 1 pi by 4 times 2x plus n into n minus 1 by 2 times 2 to the power of n minus 2 by 2 e to the power of x cos x plus n minus 2 pi by 4 times 2. The next term becomes 0. Now again here we have to simplify. This 2 and this 2 gets cancelled. That's all. Now here what all is common? Now 2 to the power of something is there in all the terms. E to the power of x is there in all the terms. So let's take these two out. E to the power of x, 2 to the power of what we'll take out? Let's take out n minus 2 by 2. n minus 2 by 2. If we take it out, what happens? Here we need to only n should remain. So minus 2 should go off. So which means square by 2. So 2 by 2. Which is nothing but 1 times ex we don't have to write. Cos. And this x square we can bring it in front. X square to x square cos x plus n pi by 4 plus. Now let's look at the second term. Second term 2x, let's bring it in front. 2x n. Now here this 2 to the power of, it will become what? 2 to the power of, here it was 2 by 2. So this will become 1 by 2. So 1 by 2 is nothing but root 2. So root 2 cos x plus n minus 1 pi by 4 plus here again in the third term n into n minus 1. Now 2 to the power of n minus 2 by 2 has already been taken out, so we don't have to write it. E to the power of x we don't have to write. So cos x plus n minus 2 pi by 4. This is the nth derivative. See, in the first statement only we apply the Leibnitz theorem, which is calculus. But rest all is just algebra. Okay, shall we do one more very quickly? Y is equal to sine inverse of x the whole square. Show that 1 minus x square yn plus 2 minus 2n plus 1 yn plus 1 minus n square yn equal to 0. We have to show this. Now here this itself gives you an idea that before you apply the Leibniz theorem you have to differentiate it twice. Okay, so let's differentiate this once. So y1 is equal to 2. First you take the exponent part. So 2 sine inverse of x, then differentiate the base. So sine inverse of x is what? 1 by square root of 1 minus x square. Okay, now 1 minus x square we can bring it to this side. 1 minus x square times y1 is equal to 2 sine inverse of x. Now this whole thing we can square both the sides. So what happens? This becomes, the square root disappears, this becomes a square, this becomes a square, and this whole thing becomes square. Sine inverse of x becomes square. Now remember, this is nothing but y. So 1 minus x square y1 square is equal to 4y. Now remember, we have differentiated once, so we need to differentiate it once more. So let's differentiate it. So when we differentiate it, what happens? 1 minus x square, let it be as it is, 2y1 y2, yes, minus, because now this bracket part we are going to differentiate. So y1 square remains as it is, and this becomes 2x equal to 4y1. Now here if you notice, in this entire thing 2y1 and 2y1 is common, so we divide it by 2y1. So then what happens? 1 minus x square, 2y1 disappears, so we are left with 2 minus 1 of the y1 disappears, 2 disappears, so we are left with y1x plus 4y. No, out of that 4, 2 remains and y1, and this 2 also we can bring it to the left hand side, so this becomes 0. Now let's apply the Leibniz theorem. So we have to apply it separately for this, separately for this. This becomes 0, so we can ignore that term. Now nc0. Let's take y2 as the first one, that is u. So we do that. So what happens? 2 times we have already differentiated, so this becomes n plus 2, and this remains as it is. Yes, that is un v plus nc1 un minus 1. So which means what? It becomes n plus 1 and v1. So we have to differentiate it 1. So this becomes minus 2x plus nc2 yn, and this becomes minus 2. Next time this will become 0. So the whole term will become 0. So we can stop at this point. So this is over. Now we have to do for this. So minus within bracket nc0 yn x. Now once differentiation has already been done, y1. So this would be n plus 1 x plus nc1 yn times 1, and this term is 0. So equal to 0. Now let's see whether any n plus 1, n plus 1. So this is like terms. This and this are like terms. So let's now simplify it. nc0 is 1, yn plus 2 times 1 minus x square plus nc1 is n. Let's bring in minus 2x in front. So minus 2xn yn plus 1. Then minus 2 nc2 is n times n minus 1 by 2. So this 2 gets cancelled. Then yn minus nc0 is 1. So yn plus 1x plus nc1 is nyn equal to 0. This minus into plus would be minus. This you have to be very careful about. Okay, so here this and this are like terms. Similarly, this and this are like terms. So yn plus 2 1 minus x square minus 2 x yn plus 1 is common. So 2n plus 1 yn plus 1 x is common, minus, what about these two? This, if we take inside a bracket, it becomes n square minus n, and to maintain that negative sign we make it plus n, yn equal to 0. So these two gets cancelled, and we are finally left with n plus 2 1 minus x square minus 2n plus 1 yn plus 1x minus n square yn, which is what we needed to show. I think that's enough for today. Bye for now.